All right, number 5, determining the end behavior of these functions. This is going to be important for us. Luckily, it's pretty easy, but it's still important nonetheless. Again, this is going to help us to visualize and see what's happening with the ends of the graph. Again, the left end and the right end of my graph. Obviously, there's going to be often some weird, funky things happening in the middle of the graph. Again, we'll worry about that as the time comes. But we need to understand that there is a distinct pattern for the ends of the graph. So, luckily, like I said, it is pattern-based, and we can essentially memorize those patterns and understand exactly what it is we're trying to do. So, a lot of this has to do with the degree. So, if we're talking about the degree of the overall function as being even, again, if you're even degree, basically what I would encourage you to just have memorized, you should already have memorized, is your parent function for a quadratic. Again, as you're already well aware, the quadratic parent function is going to be an upward opening parabola. So anytime you have an even degree, it doesn't matter if it's 2 or if it's 52 or if it's 2,000. Again, it doesn't matter. Anytime you have an even degree, the ends, the left end and the right end, are going to be going the exact same direction. So the second piece that we can look at is that leading coefficient. If the leading coefficient is positive, just like f of x equals x squared, both ends are going to be pointing upward. If that leading coefficient is negative, again, let's not overthink it. If we had f of x equals negative x squared, then we obviously had a reflection occur and would look something like this. So for that reason, now both of the ends would be still pointing in the same direction, but now they'd both be pointing down. So again, the degree being even is going to tell us that the two ends are going the exact same direction. The leading coefficient is going to tell us whether or not we're both pointing up or both pointing down. Okay? The other piece of useful information here is whether or not, or I shouldn't say whether or not, but if and when the degree is odd. If the degree is odd, we want you to consider, let's not use f of x, we'll use g of x this time, not that it probably matters, but we'll talk about x cubed. So again, only because we have this parent function totally memorized, we know exactly what this is supposed to look like, but anytime you have odd degree, the ends are going to be going in opposite direction. Again, odd degree, opposite direction. So if your leading coefficient is positive, just like it is here in the parent function g of x equals x cubed, then we consider what the cubic is going to be mimicking. Again, left side is pointing down, right side is pointing up. It doesn't matter what the degree is, so long as it's odd and the leading coefficient is positive, this is going to be your end behavior. But if and when the function has a negative leading coefficient, we know that a reflection is going to occur. Something like this is going to ensue. Okay? So again, we know that basically, long story short, is that it's going to get flipped if we have that negative out front. So that's what we're looking for here in number 5, is trying to grasp what is happening in terms of our end behavior. So here, we've got a left end, we have a right end, of course. And here in part A, we see that we have 8x squared. Not that the rest of it doesn't matter, but that's probably all that we really need to truly care about. We know that the degree is 2, that's even, so I know that my left and right ends are going to be going in the exact same direction. I can further see that the leading coefficient is positive, so I know that we're pretty much mimicking exactly what we see in the quadratic parent function. So the left end is going to be rising or going upward. The right end is going to be rising, going upward as well. Okay? In part B, g of x is equal to negative 4x cubed. I can see that the degree is 3, which is odd, of course. I can also see that the leading coefficient is negative 4. Negative tells us that we are not going to follow the exact same pattern of the cubic parent function, but instead we're going to go the exact opposite. So the left end is going to be rising or up, and the right end is going to be falling or down. Part C, we have h of x is equal to negative 2x to the 4th. So again, x to the 4th, that's going to be an even degree. So I know that my left and right ends should be going in the exact same direction. This time we can see that The leading coefficient is -2, which, again, the negative part is what really matters for us. We know that we should not follow the exact same pattern of the parent function for the quadratic. Instead, we're going to be doing the opposite. So they're not both pointing up, instead that they're both pointing down, or they're both falling, depending on how we phrase that. Okay, and then finally, again, part D, j of x is equal to 3x cubed. Again, x cubed, our highest or greatest exponent, implies that our degree is going to be 3. So 3, of course, is odd, which tells us that, again, anytime you have odd degree, that our ends are going to be moving in opposite direction. We can also see that our lead coefficient is +3. So all indications would point to mimicking exactly what we see on that parent function. So again, the left end is down, the right end is up. Again, this is just a memorization thing. Luckily, it's a pretty simple pattern, but this is a big deal for us, as we said. All right, the next few problems on this slide, we want to consider f of x equals -2x cubed plus 6x squared plus 8x minus 24. We're going to use this function f of x for number 6, 7, and 8. All right, so the first thing we want to do is figure out the max number of turns and the max number of zeros. So the key to understanding that is that my degree is 3. So if my degree is 3, we have a maximum of 2 turns. Remember, the pattern there is the number of turns is equal to your degree minus 1. So again, 3 minus 1, 2 turns. The max number of zeros, we would say 3 zeros. The correlation now is that whatever your degree is, that is your maximum number of zeros. So just like we did on the previous slide, the beginning and end behavior, again, we could see that our degree is 3, odd number. So I know that anytime we have an odd degree, that my ends are going to be moving in opposite directions. So, excuse me. So then my next step is to look at the leading coefficient. I recognize that it's negative. And as we know, as we've sketched on the previous slide, f of x equals x cubed is going to be here. So a reflection is actually going to go in the opposite direction. So for that reason, the left end is up or rising. The right end is down or falling. Okay. And then finally, we want to go ahead and graph this out. So before we make an accurate sketch, we need to know where the zeros are going to be located on this thing. So that's where we really have to get to work. Anytime we want to find the zeros, I'm going to put a 0 in for f of x, and the rest of this, -2x cubed plus 6x squared plus 8x minus 24, the rest of this, I'm now going to try to solve for x. So this is actually set up nicely for factoring by grouping. So I'm going to group the first 2 terms and the last 2 terms, and then I'm going to factor out the GCF in both cases. Again, maybe you remember this, maybe you don't. But if I were to factor out the GCF here, I'm going to factor out a -2x squared, which is going to leave me with x, not plus, but x minus 3 inside the parentheses. If I were to factor out in the next, in the next set, if I were to factor out an 8, that's going to leave me with x minus 3. So hopefully we're recognizing, oh yeah, these parentheses, they match. That's what's supposed to happen. So 0 is going to be equal to, now it's my outside stuff, so my -2x squared plus 8 times the inside stuff that matches of the x minus 3 to look something like this. All right? So just to continue on here, I would encourage you in this first piece that we have to factor out everything that we can. So I can factor out a -2. So we have 0 is equal to, again, if I were to pull a -2 out of there, think about what that's going to give us. Now we have x squared minus 4, and I still have my x minus 3. So I want to get rid of this -2, so I'm going to get this out. And hopefully we recognize what's about to happen here. 0 divided by -2 is still 0. And I'm just left with my x squared minus 4 times x minus 3. The x minus 3 is about as good as I can get. But the x squared minus 4, that's a difference of 2 squares. So I can go further. I know that x squared minus 4, again, like I said, the dots method, difference of 2 squares. You might remember your algebra 2 teachers talking about that. basically we're finding the square root. So the square root of x squared is x, goes here and here. The square root of 4 is plus and minus 2, goes here. All right. So once we have all of our factors, because that's what we have, that's great, but we need to figure out where our zeros are going to be located. So our zeros, again, if we were to think about it, if we had x plus 2 as a factor, negative 2 is a 0. If I have x minus 2 as a factor, positive 2 is a 0. If I have x minus 3 as a factor, positive 3 is going to be a 0, which is great, but we also need to consider that we're creating these points at negative 2, 0, positive 2, 0, positive 3, 0. So going back to my graph, negative 2, positive 2, and 3, we're going to plot those points in their respective locations. So negative 2, positive 2, 3. Now we need to consider all this other stuff that we've already discussed. We said that the left end was going to be going up, the right end was going to be going down. We've also discussed actually, I shouldn't say that. We haven't discussed yet. In terms of my zeros, I don't see any repetition. So for that reason, we have to assume that the multiplicity is 1 in each case, which means that we're going to be going through all of these. So we could determine that we go through here, through here, through here, and at this point, we don't fully care where exactly these points are located, but we could simply and easily figure out that y-intercept, okay? So the reason why I even point this out is that if we put a 0 in for y to find the x-intercepts, we could put a 0 in for x to find the y-intercepts. So what I mean by that is that if we were to say f of x, in fact, I'm actually even going to do it in terms of calling this y, and say that that's equal to negative 2 times x, but I'm going to let that be 0 cubed, plus 6 times x, which is 0 squared, plus 8 times x, which is 0, minus 24. Again, we can clean this up because we have 0, 0, 0. Pretty quickly, we can determine that y equals negative 24. So as you can see, my sketch is not very properly done because my y-intercept would be clear down here at negative 24. But if we were looking to make the most precise graph possible, that's how we would do it. But for our purposes tomorrow, I think we'll be okay. All right, so last that we've got here, number 9. Again, we're going to try to do some long division in number 9, part A. The reason we have to do long division is because with this divisor, I cannot do synthetic division. So 6x cubed minus 16x squared plus 17x minus 6. Racing the end of this podcast here. I've got my 3x minus 2. So 3x goes into 6x cubed. We'd say 2x squared times. When I multiply 2x times 3x minus 2, that's going to give me 6x cubed minus 4x squared. We have to remember that I'm subtracting this, which really means that I have to add the opposite. So these are going to cancel, which is going to give me negative 12x squared, dropping my 17x, excuse me, to look like this. All right, so 3x goes into negative 12x squared. We'd say negative 4x times. Now when I multiply, that's going to give me negative 12x squared plus 8x. But remember, I'm subtracting this binomial, so I have to add the opposites. My 12x squareds cancel. 17x minus 9, or minus 8x, excuse me, is going to give me 9x, and I drop down my minus 6. Lastly, 3x goes into 9x exactly 3 times. Or multiply, that will give me 9x minus 6. When I subtract that binomial, again, we're adding the opposites, and 0 is our remainder, which is fantastic news, because now I know that my final answer is 2x squared minus 4x plus 3. We're going to look at 3. We're going to have to deal with it. All right, last up that we have, again, by the way, on your quizzes tomorrow, again, thanks to Eli Feakin, he gave us the idea of make a diamond, put a circle inside of it. That's going to be the symbol that we want you to put in the top left corner. All right, so in part B, we can absolutely use synthetic division. If x minus 4 is that divisor, positive 4 is that potential 0. We've got 3, negative 12, 5, negative 18. The pattern for our synthetic division, we'll see how fast we can do this. If I drop the 3, multiply to get 12, add to get 0, multiply to get 0, add to get 5, multiply to get 20, add to get 2. As we can see, that might seem like a problem, but we have a final answer of 3x squared plus 0x plus 5 plus 2 over, remember x minus 4 was that divisor.